Hi guys, welcome to this tutorial on esoteric tech. Thank you guys for joining. This tutorial is going to be slightly different than the Golang tutorials I've done so far. This is going to be the first of a multi-part series covering data structures and algorithms in Go. The videos I've created so far have really focused on the features and the nuances of the Go programming languages. But one of the reasons you learn those type of things is to be able to create data structures like the one I'll be discussing today. In addition, data structures in general are really just an important part of programming, which is one of the reasons you see them often appearing on programming assessments required by tech companies. Major companies like Facebook, Amazon, Google, and Netflix are notorious for requiring their candidates to have an in-depth knowledge of data structures and algorithm, regardless of the programming language that you're working with. So this is something that will undoubtedly help you in your career, and understanding these really gives you kind of a foundation to address common programming challenges and problems that will pop up over and over again throughout your development career. So the data structure I'll be discussing in this video is a linked list. And linked list is really a common starting point when learning data structures, and that's kind of because it's the most simplistic. I'll explain what they are, when to use them. I'll compare them to arrays, and then I'll go into details of how to actually create them. And as always, if you find this video to be helpful and informative, please do subscribe. I'll be coming out with many more videos with the goal of helping you to prepare and excel in your software development career. So let's get started. So what you see here is really the textbook definition of a linked list. A linear data structure in which the elements are not stored at contiguous memory locations. And the second part of that is really the most important piece of this definition, which is that the elements are not stored in contiguous memory locations. And this means that you can have individual elements of the linked list stored throughout different places in memory, but it all works because each element knows the memory address of the next element in the list, which we'll discuss in a minute. Linked lists are, of course, not the only linear data structure. Another common linear data structure is an array, which leads to the question, when would you use an array versus a linked list? So let's first talk about what an array is. An array is a linear data structure whose elements are stored in a contiguous memory location. And there are some pros and cons to this feature of arrays. One advantage is that you can access elements at a specific index much faster than you would with a linked list. In fact, this is one of the drawbacks of a linked list. And that advantage of an array is really due to that contiguous feature. So this is why you would only need to reference the array and the index to access an element of that array. However, you experience the downside of an array when you have to unexpectedly add additional elements to that array. So, for example, let's assume that each one of these pink values are elements of the same array, and the element in yellow here represents some piece of data in memory that has nothing to do with that array at all. If I wanted to add an element to the beginning of this array, I really can't easily do that because I'd end up overwriting this unrelated piece of data stored in memory right next to it. And when this occurs, the only solution is to shift the entire array over, which computationally is an expensive operation. And this really touches on the purpose of these data structures and algorithms that I'll be covering. The purpose of these structures is not just to accomplish a goal. The purpose of a linked list is not just to create a list. There are obviously multiple ways you could do that. It's about understanding the application requirements and using the most efficient data structure to satisfy that use case. And an array is not always the most efficient way. Sometimes it is, sometimes it's not. The same is true for linked lists. And so in regards to an array, you would run into a similar issue if you initialize an array, but later on wanted to insert a new value into that array. And this arises because the size of the array is initialized as soon as you create it. So in summary, an array is useful when you have to modify a specific element, but if you believe you're going to have to insert or delete elements at a later time, a linked list might be more appropriate. And the last piece that I'll say about efficiency is that When we're discussing data structures and algorithms, there's a standard way of representing the efficiency of certain operations in regards to the time and memory that gets consumed. And this is referred to as big O notation. I won't go too deep into this because big O notation could be an entire video to itself, and maybe I'll cover that at a later time. If you guys do want to see that, just let me know in the comments. But for now, just know that certain notations represent certain measurements of efficiency. There are two primary categories when discussing big O notation, which is time complexity and space complexity. You can see we have two types of notations here, which is O of 1 and O of n. So O of 1 represents a constant time. So what we're saying here is that the time it takes to insert or delete an item from a linked list is always the same regardless of the number of items in the list. And the O of n represents a linear relationships. This means that the memory space required to store a linked list increases linearly with the amount of items in the list, which of course makes sense. So that's all I'll say about that. If you look at a different data structure, these representations of time complexity and space complexity will be different notations. And so these are really kind of key features or key characteristics to remember when you're learning about algorithms. Let's discuss this concept of nodes now. I've referred to this idea of elements a few times, but when we're discussing linked lists, each element is really referred to as a node, and a node is composed of two parts. The first part is the data that you want to store, which can be really any type of data. And the second part is a pointer or reference to the next node in the list. So this image here shows how this concept works within memory. We have 4 nodes here, each holding an integer value for their data. And each one points to the next node in the list. If you want to access the data of any particular node, then we have to traverse this list going from one node to the next. So we start with 45 and then go to 98 and 14 and so forth. One of the features of a linked list is the presence of what's called a head node. And this refers to the first node in the list. And it's more than just a nickname. This is actually a special identifier that we place on the first node so that we know where the list starts. And in some lists, you can actually include a tail identifier too, so that you can easily identify the last node in the list. If we wanted to add an additional element to this list here, what we do is create another node, add the appropriate data, and add a reference to the next node in the list, which was previously the head. And then we move that head identifier to this new node to indicate that this is now the start of the list. And lastly, I won't really show this in code today, but there is a concept of a doubly linked list in which a node not only points to the next node, but also points to the previous node in the list. So today I'm just going to be showing you a singly linked list, but once you guys get the concept of linked lists in general, being able to make these types of changes really becomes trivial. So let's hop over to the code and I'll show you guys how to create one. Okay, so what I'm going to do here is create a linked list along with some receiver functions that allow me to add nodes, delete nodes, and print out all the values of each node stored within a linked list. If you've been able to follow along with me up to this point, which has all been theory, following along in the code really shouldn't be too difficult for you as long as you have experience with Go or really any other programming language, because we're not doing anything crazy here. It's pretty straightforward. We're just literally just putting everything I just explained into code. So one of the first things I mentioned about linked lists was this idea of a node, and they compose the elements of a linked list. So I'm going to go ahead and define that here. So a node is going to be a new type. And I mentioned that a node is composed of 2 components, and that is the data that's stored in the node and a reference to the next node in the list. So I've got this next field, and then I'm going to have, actually the next field is going to be data, and that's going to store an integer. And I'm just keeping it simple with an integer. Like I said, a node could, store any type of data. I could have data be, a storage for some completely different type in this case, but I'm just using an integer. So I've got the node defined, and then I want to define a linked list actually. So this is going to be another type called linked list, and this is going to have a head, and that's kind of that identifier that I said points to the first node in list. And so that holds a pointer to a node, and then this is going to have a property on it called length, which stores an integer. One thing you might be thinking about this linked list data type, it's that it's surprisingly simple because it's not really representative of maybe what you're used to when you're thinking of a list. Like I said, it's really just identifying the first element of the list, and from there it's pretty much like breadcrumbs. Each node points to the next one in the list. So in this trail of breadcrumbs or nodes, you only need the first one, and then from there you kind of work your way through it. So I'll now get into the logic of these receiver functions, and before I do, I want to say that this is not the only way that you can implement the logic for a linked list. If you Google linked lists, you will find 20, 30, 40, maybe even more different implementations of these methods here. And I'm definitely not bold enough to say that mine's is the best. It's just one way to achieve the desired outcome of these individual methods. And so there are some functions that, or some implementations where people will return error statements from their functions if something doesn't pan out the way that it should. I'm not going to do that here. I'm just showing you guys the basic knowledge, and I'll leave that up to you to perfect it if you want to change something about it. But the first function that we're going to look at, or receiver method that I'm going to implement, is the prepend function. I said I wanted a function that allowed me to add nodes to the list. So I'm going to go ahead and type that out, and then I'll explain it. What I've done here is create a prepend function that accepts a value, so accepts this data and creates a new node with this data and adds it to the list. And this is a function where, like I said, I've seen different iterations or different implementations of this. I've seen some prepend functions that accept a new node and then just add the node to the list. And so in that case, you actually have to initialize an instance of this node type and pass it in. But in my implementation, I want this function to construct the node for you from the passed in value. And so that's just what I'm doing here on this first line. I'm creating an instance of this node with that passed in value as the data. And then the next thing I check to see is, are we adding this node to a list that already exists, or is this node going to be the first one in the list? And that's what it's checking here. We're saying if L.head is not equal to nil. Well, L.head holds a reference to the first node in that list. So if it's not equal to nil, then what we're saying is there's already a first node, and we want to prepend this. We want to create a node that will in turn be the first node. It's going to replace that one. And so what we're doing here is saying, okay, if this is not the first node in the list, we want it to be. So new node.next, which is the one that I just created, we're saying we want that next field, this pointer to the next node of the list, we want that to point to the one that was previously the first one in the list. And so that's what we're saying here. We're creating a pointer here, and then we're moving the head to the new node. So now we're putting this new node in this field here, and then we're increasing the length by 1. And then we've got this else statement, which is for situations in which this is the very first node of the list. So we're just saying L.head is equal to the new node, and we're increasing the length of the list by 1 and then returning. Hopefully everything I explained right there made sense, but if it did not, feel free to pause and rewind this video, listen to it again, make sure it makes sense before moving on. The next function that I want to implement is a receiver function that will print out all the values stored in the list. And so again, this is going to be a receiver function of the linked list, and we're going to call it print list. Okay, so here we have our print function, and similar to what I said in the method above, the Prepend method up here, I said that if the head of this linked list didn't have a value, then that means there are no nodes in the list, right? And so we're performing the same check here, because if there's no head, then there's nothing to print. So we check to see if it's nil. If it is, then we just return from this function. And this is an area where I said there's kind of some room for different types of implementations. If I was trying to make this perfect, maybe what I'd return here is some type of error along with a message saying, you know, nothing to print or no nodes to print or something like that. But moving on, if this value is not equal to nil, that means there is at least one node. So first thing we're going to do is going to say, we're going to create a variable and say the current node is equal to the first node in the list. And then we're going to iterate through the list. We're actually going to traverse through it. And we're going to keep on traversing until this current node is equal to nil. So this is essentially a for loop. And we're saying while the current node is not equal to nil, what we're going to do is set the current node to the next node that the current node references, right? And so we're looking at a particular node, we're traversing through it, and we're saying, okay, let's set this current node to the reference stored in this node. And so we keep on traversing down the list, and once we get to the last one, well, that last one on the list isn't pointing to anything. So this current node is going to be set to basically a nil value, and then we realize, okay, we've hit the last one. And so along this way, when we're iterating through this while statement, we're printing out every value stored in the node that we're kind of hitting along the way. And so that's kind of the logic behind this print list function. Again, if that doesn't make sense, feel free to rewind this video, because that's kind of the difficulty in some of these data structures. Is it's not hard logic, it's just you kind of have to listen to it a couple times before you get it. So if that makes sense, I'll go ahead and move on. The last receiver function I'm going to create here is a delete function that allows us to delete nodes from the list. Just like above, I'm going to use func along with passing in a pointer to a linked list, and then similar to the prepend function, this is going to be a receiver method that takes in a value, and so then it's going to find the node with that value and delete that from the list. Okay, so if you've understood everything I've said so far, congratulations. This one here, though, is probably going to be the most difficult of all the functions that I've showed you, and to me, I think it's the most difficult one for linked list, period. And I'll take it kind of slow. Similar to the other ones, I start out making sure that there are actually values in the list, and you can see here that I actually did that in a different way here. I actually just checked the length of the list, and I did that just to show you, again, there are different ways to go about this, and you could argue, well, I didn't even need to include a length variable as a field of the linked list, but maybe, you know, at a later time I want to add some type of receiver function that simply prints out the length of the list, and then that variable would come in handy. But like I said, it's up to you. It's up to the requirements and the use case of your application. So we check to see, do we have values? If we do, let's go ahead and move on. And keep in mind, the goal of this function, what it does here, it takes in a value and it deletes the node, it removes it from the list if it has that value. And it only does that for the first one that it encounters. And so the first thing that we check is the first node in the list. We say if the data is equal to the value that was passed in, well, then we set the head to the next node in the list, which is the one that's referenced by the previous head here, right? And so we go ahead and just move the head over one and reduce the length of the list by 1. So here is where I think the logic gets a little confusing. So I guess one thing that's important to explain is whenever you see these while loops in these receiver functions, most of the time what it's doing is traversing the list. Typically it has some type of variable that keeps on being updated with the next node in the list, and it's normally like checking some type of value, and that's kind of the process of traversing. Well, when we're deleting something from the list, this presents an interesting problem, because if we were to update that variable to hold the node that actually has the value that we want to remove from the list, how would we bridge the gap? And what I'm saying is, because this is a singly linked list, the pointers only go in one direction. It only goes from the beginning to the end of the list. We can't traverse backwards. So if I update this variable to be the node that we want to delete, how do I make the reference or the pointer of the previous node point to the next node? Because I can't access the previous node anymore because I've already passed it. And so here what we do is we cheat a little bit. We kind of peek ahead. And so what we do is we have this variable called previous to delete. And so what we're saying is we're actually one node before the one that we may have to delete. We're saying while the previous to delete dot next dot data is not equal to the value. So if the next one in the list is not holding the value that we want to remove, and I'm going to skip this statement right here, I'm going to come back to this, but if it's not holding that value, we're going to go ahead and go to the next one. The previous to delete is going to be equal to previous to delete dot next. So it's like every single time we're on the next node, we're examining the next one in the list. So as long as that next one is not the one I'm going to delete, it's safe for us to move on to that and examine the next one. And we add this if statement here because we're saying if the previous to delete dot next is equal to nil, well, that means we've reached the head, or I'm sorry, that means we've reached the end of our list and we didn't find this value at all. We never hit it, and so we just return. But if we find that value, keep in mind, we're going to keep on iterating through this list, keep on iterating this while loop until the next node has the value that we want to delete. And once we find that, then we bridge that gap, right? We're saying the previous to delete dot next is equal previous to delete dot next. So it's essentially we've cut out that node that we want to delete, and we've just kind of spanned the pointer from the current node to 2 nodes ahead, and then we decrease the length by 1. Again, hopefully all of that made sense. The last thing that I'm going to do is just put all of this to the test. I'm going to test out all of this logic and make sure that it works. And so I'm going to create my func main here. And then what I'll do is actually initialize a new list. So my list is equal to linked list. And so here I've got an instance of this linked list, but it doesn't have a head and it doesn't have a length. And so what I'm going to do is call those prepend functions and pass in values to start generating nodes for that list. So again, what I've done here is initialize a list and then call these prepend functions, passing in values which create nodes on this list. And then I'm just going to print out the list here. So I'll run this statement. And then we can see the values printing out. And of course, this is the order of the linked list, with 57 being the head, because that was the last one that was prepended to this list. And then let's just make sure that the delete function actually works. So I will call my list dot delete with a value, and I'm going to delete the node that has a value of 78. And then I'll call that print list function again. And so what we should see here is pretty much all the same, except it's going to be missing the node here with the 78. So I'll run that. And there we see it. We can see that we only have 3 nodes here. And so this is pretty much all there is to a linked list. Like I said, there are plenty more functions that you could have. There are functions, you could have a function that appends a value to the end of the list. Like I said, you could have a function that simply traverses the list looking for a certain value and returns the position. There are lots of things, but all of them would pretty much implement this same type of logic that I've showed you here. So if you guys have any questions, please let me know. Again, as I said, this is the first of many Golang tutorials on data structures and algorithms. Please do subscribe. Let me know your thoughts. And I hope to see you in the next video here on Esoteric Tech. Thanks for watching. Bye.